Hello, my name is Joan Triay. Welcome to this presentation for the Layer 1 to 3 World Congress. The presentation is titled 5G and NFV Native Network. And this is part of the work that we have been doing in the ETSI NFV ISG. So the presentation has the following outline. I will provide a brief introduction first to the NFV architectural framework, and then I will briefly introduce the 5G network characteristics. Thereafter, I will go more in detail on doing the profile of NFV to support the deployment of 5G networks, and more precisely about the characteristics I will highlight, and I will conclude the presentation afterwards. So, as a brief introduction of the framework of ETSI NFV, which we use for this profiling, I would like to highlight what is the evolution that the framework has undergone in the last few releases. Probably many of you are already familiar with the baseline of the release 2. So here I have depicted the actual architectural framework that we delivered back in 2014. It is composed of different functional blocks, and I will not provide details about them because these are heavily already documented in the ETSI NFV specifications and also in many other materials available on the internet, for instance. I just want to highlight what are the main additions to the framework that have been done in Release 3 and Release 4. In Release 3, we added a new reference point in between the NFVOs. The purpose of this reference point is to enable the connectivity of the NFVOs that are deployed on different administrative domains. And the purpose of that is to enable the support of deploying multi-domain network services. Another addition to the framework was to support multi-site connectivity service. The purpose of it is to enable the deployment of the network services and the VNFs on different NFVI POPs or sites. For that purpose, we introduced a new functional block called the One Infrastructure Manager, which can be connected to the NFVO or also be connected to other OSS DSS systems. In Release 4, we basically we did an evolution of the framework to enable more cloud-enabled deployments. For that purpose, we introduced few new functions into the system, and also new type of infrastructure resources or services, precisely for the orchestration and management of containers. I will not provide details about these functions and these new type of resources, because a colleague of mine later on will provide a dedicated presentation about these specific enhancements. Another extension which is currently in progress in ETSI NFV is the addition of the function that provides the capability to perform the lifecycle management of these new type of infrastructures, which we call the CCM. And this will also be briefly introduced in a subsequent presentation. So the purpose that I introduced the framework is because this is also the baseline for the profiling that we have done when it comes to determine the support of NFV for 5G networks. So for 5G networks, we have taken as a baseline the system that has been defined in 3GPP. The reason of that is because this is one of the most mainstream and global 5G systems that will be realized or are realized. And as defined by the 3GPP, the network is composed of the access network, which can have or include the connectivity, the radio connectivity according to their specifications, or also non-3GPP access network technologies, the core network and the UEs, and also, of course, the connectivity to other data networks. As of 3GPP release 16, the 5G system control plane is also designed as an SPA. And if one downloads the specifications from FreeGPP will also realize from the very beginning that in their design of the system, they also acknowledge very clearly that they designed the system in a way to enable its deployment using NFV and SDF. 5G networks are characterized by many new features. Some of them are also inherited from previous releases, like the roaming capabilities. The list of characteristics here that I depict on this slide is not meant to be exhaustive. One of the reasons, of course, is because 3GPP also continuously evolves the system by adding new features. But I wanted to depict this list of characteristics as the baseline that we have used for the profiling in ETSI NFV. And also because these characteristics are quite relevant on new aspects that have been introduced in 5G, like, for example, network slicing or the service space architectures. The purpose of the study is precisely to determine how, in support of these characteristics of 5G networks, how the NFV framework helps realizing this end goal. And in cases that there are potential enhancements to the system, to identify the parts that could be enhanced to increase this support. So, the profiling of the NFV for the 5G. More information is available on very soon to be published GR or study item. It is the number ETSI GR NFV IFA 037. And the scope of this work item in ETSI NFV has been precisely to profile the current NFV architectural framework, its capabilities and features, and determine how well this framework can realize the deployment of the 5G networks. I will not go in detail of showcasing all the different solutions that are documented in this GR. So I welcome you to download at a later time this document and dive deep into all the potential solutions that we have documented. In the following slides, I will just provide a brief summary of some of them. So the first one I wanted to illustrate is the network function modularization. This is something new also in 3GPP, from 3GPP point of view, because they do not only detail in the 5G systems the network functions, but also network function services. So the idea of this activity in the profiling was to check how the different NFV constructs, namely the network servers, the VNFs, and the VNF components, can help realize the deployment of these concepts from 3GPP. On the left side of the figure, I depict what is the main abstraction view of NFV, including the VNF components, the VNFs, the network services, which can also be nested into higher level composite network services. And on the right side, I show what is the view from 3GPP, which is basically the show of the network function and the network function services. So we can play with these two levels of constructs and determine what are the possible realizations. The first one, which is obvious, is map one-to-one of VNF concept with network function concept. This is a straightforward mapping. Another mapping that is not so straightforward, but it's also possible from NFV point of view, is that VNF realizes a specified 5G system network function service. This is not contrary to the concepts of VNF, because in VNF, as defined in ETSI NFV, is a well-defined network function capability that has well-defined interfaces. And this is precisely what has been done in 3GPP with the definition of the network function services. And the way that the network function then can be delivered to the operator for its deployment can be realized composing these new network function services as VNFs into a higher level network service, which can then also be nested into a higher level or composite network service that can realize the whole 5G system. The third mapping that I wanted to highlight is the one that allows for actually composing more than one network function and be delivered as a virtualized network function. And this is also possible according to our definitions in ETSI NFV. As you can see, the mappings are quite flexible. However, we also found during the analysis that we could improve in certain aspects these specifications, for instance, on how to improve the relationship or the information available to the operator about the relationship of network function services with the scaling aspects, or also providing more flexibility in the onboarding processes of the network service descriptors and the VNF packages. The second characteristic I want to present about is the SBA. So as you might well be aware, the 5G system according to 3GPP, and more concrete, the core network control plane has been defined following SBA approach. We also have, in our case in NFV, possible realizations for this SBA. According to 3GPP, different modes of communication have been defined. Direct communication, which does not involve any service mesh capability in the middle, and indirect communication by means of the new function called service communication proxy. So the purpose of our profiling was to check how we can fulfill these different modes of communication. And for the cases of the direct communication, we found that we can use the actual and already defined concept of the NFV virtual links to do this realization of the direct communication. The solution is quite simple because in virtual links, according to ETSI NFV, are also the mechanisms that we enable this direct communication. We enable the connectivity in between the constituents of the network services. For the realization of the SCP, what we determine is that we can use also different NFV objects like the VNFs, virtual links, and the network forwarding paths to realize such type of connectivity. And we also analyze solutions on how we can provide the deployment of different parts of this service communication proxy by using container-based VNFs. So I will show in the following slide just three specific solutions that have been analyzed. And in the IFA 37 that I introduced previously, there are many more. The first one I wanted to highlight is the one where we enable this direct communication mode in 3GPP. For that purpose, we can use the virtual link, as I mentioned before. In order to provide extended capabilities of how this communication can happen, we also found that we could further enhance the virtual link to provide additional capabilities, such as naming resolution capabilities. The second solution I want to highlight is the one where we implement the SCP using the virtual link concept. In this case, we can also enhance the virtual links to provide additional capabilities like load balancing and name resolution. And the third solution I want to highlight also on this slide is the case of providing the deployment of the service mesh agent for the SCPs. In this case, we can have two sub-solutions. One, which is depicted at the bottom, where the actual service agents that are used for the data and the control plane communication of the SCP are delivered as a specific VNF components. Another solution is the one depicted on the top, where we, as we define in ETSI NFV, can offer platform capabilities to the VNF designers that can be reusable. Therefore, they don't have to care about the integration of these specific agents because they could be offered by the platform. In this case, the concept that we use in ETSI NFV is named the VNF Common Dedicated Services. In the case of the realization of the SBA approach, we also found that we could further improve our specifications, and we are in the process of doing that. For example, on providing inventory of these VNF Common Dedicated Services, as I mentioned in some of the solutions as well, to enhance the virtual links, to have additional capabilities, and also overall to ensure that the NFV Mano can perform the management and orchestration capabilities for the deployment of the different solutions of service mesh. The next characteristic I want to present about is the network slicing. Network slicing has also been highlighted as one of the main new features of 5G. And I would say that the network slicing as defined in 5G inherits a lot about the concepts that were already created some time ago in ETSI NFV. Here, I would determine that NFV provides a native support of realization of network slicing by means of the constructs we already defined, such as the network services. According to the mapping that we have established with the 3GPP specifications, we are mapping the network services in our ETSI NFV framework with the network slice subnet concept that has also been introduced in the management specifications of 3GPP. Basically, in 3GPP, the realization or deployment of a network slice is realized by different portions of network slice subnets, which in the end-to-end can realize this network slice. In the next slide, I will show different potential solutions on how these mappings can be performed. The first figure on the left is a case where we have network services, which is the mode that we do the resource fulfillment of the network slice. We have network services that are mapped one-to-one to respective network slice subnets. According to the 3GPP view, they also have a network slice subnet, which is the umbrella subnet that composes the underlying subnets. In that case, we also have a one-to-one correspondent construct or deployed network service in the ETSI NFV framework. This solution considers the capability that since we have a composite network service for the whole network slice, ETSI NFV framework can also be used to deliver the connectivity in between the different subnets, because we can also express requirements of connectivity precisely between these subnets, which can then also be expressed in the network service descriptors for this composite NSS. The example in the middle is similar to the previous one, but as you might observe, there is no composite network service on top of the different three ones that are shown here in the picture. In this case, the assumption is that the connectivity requirements that are expressed or needed for the connectivity between the different network slice subnets is not of concern for the NFV Mano, therefore are assumed to be pre-provisioned or provisioned by other means. This case is also possible, so we also wanted to highlight it as a possible realization indeed. The last figure on the right side is an example where we show that we do not need to restrict one-to-one mapping of network slice subnet to network services. We can also have one single network service that is used to deploy more than one network slice subnet. The benefit also of this solution is that we can also consider the connectivity that is needed in between the different network slice subnets to be also expressed and fulfilled by the network service that is deployed via the NFV Mano. In terms of how to handle all these cases, as I said, ETSI NFV concepts and specifications are already quite natively supporting this capability of 5G systems. However, we found that we could potentially improve the specifications, for instance, when we need to consider precisely the case of pre-provisioned connectivity. The next characteristic I want to highlight is the one about the distribution of services across the network. According to the 3GPP specifications, a network function instance can be deployed as distributed, redundant, stateless, Also for the case of the NF set. In this case, what I want to highlight is that NFV has also provided quite natively support to consider many different types of deployments by the operators and provide the flexibility on how to express requirements of relationships in between the components or constituents of the network, and to actually also indicate specifically where to deploy certain entities. We have, for example, the attributes of or parameters of affinities and anti-affinities, and we have also defined in our specifications the placement location constraints for that purpose. In this case, we also found that potentially we could have some further enhancements in ETSI NFV specifications, not for the case of the deployment of the VNFs as such, but when we need to consider, for example, certain mappings of VNFs to the different concepts of 3GPP, like the NF and the NF services, we could enhance our specifications for providing further granular constraints on how to deploy specific parts of the VNF. The last characteristic I want to introduce is about the stateless network function. This is also one of the key aspects realized in the 5G system. Here, the idea is to perform the separation of the processing of the state from the entities that actually store such a state. The 3GPP system, according to their specifications, have also been enhanced. One aspect that was enhanced on 3GPP side is by the addition of specific new functions for the purpose of storing a state. We have the unstructured data storage function, the unified data management and unified data repository. And in this case, we also try to consider these specific enhancements on how NFV can realize such type of feature. The NFV case, in the NFV case, we also had a very native support of mechanisms of compute and storage separation. For example, we have from the very beginning defined different type of virtualized resources. We have virtualized compute, which can be used for the processing, of course, and virtualized storage, which can be used for the storage of the state. We also have the concepts of the componentization of VNFs and network surfaces, which can also be leveraged to provide more flexibility on the design on how to decouple the state processing from its storage. And as I introduced also in the previous characteristic, we also have affinities and anti-affinities and placement constraints, which can also be used to ensure that there is actual separation of these different storage and compute resources to guarantee, for example, certain reliability. Some of the solutions that are analyzed in the IFA 37, for instance, the example on the left tries to depict when a VNF designer has the capability or offered capability to design the VNF in a way that some components are responsible or function specifically for processing the state, and others used for storing the state. This is indeed possible according to our specifications because we have the capability to associate a specific virtual storage to VNF components. The example in the middle is the solution where we have the capability to define a VNF, which is the VNF that realizes those specific functions in the 3GPP system, like the UDR and the UDSF. In that case, those functions will be the ones that will claim virtual storage resources for keeping a state, while some other functions that are determined to be stateless will not need such type of resources. And this is also possible according to the specifications in ETSI NFV. The last example is similar to the previous ones, but here we also leverage the concepts I introduced previously of the VNF common services or VNF dedicated services, because we also have the possibility that the platform itself can offer storage capabilities. And this could be also leveraged by the VNF designer. Therefore, they do not need to explicitly create components that use virtual storage. They can also just reuse the virtual storage provided by the platform. In this case, we also found that we could further improve the ETSI NFV specifications, for instance, on providing more independent management of the virtualized storage resources when they are associated to VNF components. And also, we could improve our specifications to enable explicit reuse of storage among different virtualized network functions. So I hope that I provided a quick summary of some of the characteristics that we have analyzed and profiled. And I just want to conclude highlighting some of the recommendations that also we derived based on this effort. This is a very high-level summary of some of them, just only the ones that are associated to different characteristics analysis that I have provided in this presentation. Many more are documented in the ETSI NFV IFA 37 that I introduced previously. So for instance, we have determined that we could improve our architectural framework to support the inventory of the VNF common and dedicated services as new platform capabilities that can be offered to VNF designers, like for example, the case that we could have capabilities of storage. We also found that we could further improve the functionalities of existing functional blocks in the ETSI NFV architectural framework. For instance, the VNFM to be able to express additional management of VNF external connectivity. This is indeed already possible for certain types of connectivity, but not for all the ones that are considered in 5G networks. We could also enhance the VNFM and the NFVO indeed also to manage these dependencies of the VNFs and the network services towards the platform enabled capabilities of VNF common and dedicated services. We also found that we could improve descriptors and other information objects we have, like for example, the NSD on providing more flexibility on how to express dependencies in between the VNFs. Or we could also enhance the VNFTs on providing a placeholder to define requirements for the VNF designer on precisely those platform-enabled capabilities, like for example, storage or service mesh communication. And we also found that we could improve here and there some of the interfaces and their associated information models, for example, to provide naming-related information, providing further granular location constraints, and so on. So, in conclusion, I would like to conclude this presentation highlighting again the efforts that have been done as part of the IFA 37 in ETSI NFV, whose purpose was precisely to perform an analysis of the 5G network capabilities and determine how NFV technologies and the NFV architectural framework can support the implementation and deployment of this type of networks. And we have determined in our analysis that NFV already provides quite an outstanding support for the implementation and deploying of the 5G networks, not just only based on paper analysis, but also on actual commercialization that is happening already right now. And we also found that, of course, as technology evolves and new requirements come in and use cases, we could further improve certain aspects of our specifications or the framework, for example, to provide additional service mesh capabilities or to enhance the integration of these capabilities into the NFV stack. And with that, thanks a lot for your attention. If you are interested, you can also follow any of the links for further information on any of the work that we perform in ETSI NFV. And I would like to thank your attendance. Thank you.